Anyway, my name is Brandon Simmons. I live in Richmond, Virginia. Right now I write Haskell for a living, for work. I work for a company called Signalvine. It's based in Alexandria, Virginia. So I guess the point of this talk is just to share some things that I've learned writing this bloom filter that I'm calling unagi-bloomfilter. And I find that I learn a lot of things from writing libraries, and so it's just going to be kind of a mixed bag of stuff that I think is interesting. So here's kind of the outline. I'll talk about bloom filters kind of briefly, assuming a lot of people are familiar with them. Talk about this variant called Bloom1 that I chose for this library. I'll talk about the dependencies that I'm using and that are going to be useful if you want to do similar kind of work in Haskell. We'll go through the code and the API and just jump around and talk about some maybe interesting points. I'll also talk about another library I wrote as a kind of a dependency because I needed it for this library called hashabler, which is a hashing library. Probably won't talk about performance very much because I just started doing that like at 11 o'clock last night and I don't have much to say about it. And then like future work that I want to do and want help with. Another reason I wanted to give this talk is just to get ideas from all of you too. It's always interesting to think about something by yourself for a while and then get other people's feedback. So how many people are very comfortable with like traditional bloom filters and how they're implemented? Cool, so a lot of people, it's new to them. That's really awesome. I didn't really practice explaining bloom filters because I thought everyone would raise their hand. So anyway, a bloom filter is a set. So the API it gives you is an insert and lookup. Lookups can return a false positive. In other words, you can ask the bloom filter, is this object in the set? And it can answer certainly not, or probably yes, or maybe yes. So a lot of the scholarship that has gone into like studying bloom filters, the papers and stuff, are about kind of determining for which parameters how the false positive rate changes and stuff like that. But they're pretty simple to understand, as you'll hopefully see. So bloom filters are hash-based. So in order to insert and look up an element, you first take a hash of that element. So if you're not familiar with the hash function, you provide it arbitrary data, and it will crunch it up into a number, just like maybe 64 bits. It's compact, which means that it's able to store a lot of data in a very small number of bits relative to the number of elements. And it's constant space, so after you create the bloom filter initially, it doesn't grow as you add elements to it, so it uses no more memory. However, I won't show that right now, sorry. So however, as you add more elements, the false positive rate grows. So here's a little illustration of, so this is basically illustrating 3 inserts of elements into a bloom filter, and then on the bottom that's representing a lookup. So your bloom filter is fundamentally just an array of bits. So this particular bloom filter I'm showing uses an 18-bit array, which is a very weird number and small. It also uses 3 hash functions per, it uses 3 hash functions. And so those numbers 18 and 3, those are like knobs that you can turn. They're parameters of the bloom filter. And you can change them and get different false positive rates for different numbers of inserts and stuff. So what you do to insert an element into a bloom filter is you hash it, in this case 3 times. And so you have 3 independent hash functions, so they have to be unrelated to each other. And each of those hash functions maps all the data in your thing that you're inserting, which could be, say it's a word. It hashes that data and maps it into a number between 1 and 18. So you do that 3 times independently. And then to insert, you just find each of those bits that are pointed to by the respective hash functions, and you set them to 1. And then, so that's showing X, Y, and Z all inserted into the Bloom filter. Does that all make sense so far? Okay, cool. And then, so now we're doing a lookup of W. We hash the item in the exact same way using the same hash functions, and then we look up each of the 3 bits. And if any of them is 0, which in this case it is, you can see that rightmost one is a 0, we know that the element was never inserted. So that's a true negative. And does that make sense to everyone, why that would be the case? So if instead of that 0 right there, the 3rd hash had pointed to the 1, the next one over, you might see I can't tell if that would be a false positive or a true positive, but you can see how there can be bits that are inserted from other elements, and say if this Bloom filter starts to fill up with 1 bits, you'll start to see more false positives. So there's no way of determining, because you lose the actual element after you hash it, whether it's a false positive or a true positive. So kind of obvious properties of this are that you can insert arbitrarily large keys into it, because they all just turn into these hashes and we set the same number of bits. And you can insert an arbitrary number of elements, although eventually it'll fill all to 1. And then everything will be like a true positive or a false positive. It'll only return positives on your queries. Yeah, so forgot I could walk. So yeah, so this is negative. So you see we hashed with our 3 different hash functions, and this one was not set. So because we're using the same exact, it's a deterministic procedure, these hash values, if we had inserted W, yeah, so this is, so each of the arrows represents a function from your element to a number between 1 and through 18 in this case, because there's 18.
1 bit?
Yeah. Mm-hmm.
Okay. What's the point of it?
What's the point of the Bloom filter?
Yeah, what's the point to correspond, something to 1 bit?
Sorry, could you ask your question again? What are you asking? Like, sorry, I guess I don't understand. I'm probably not explaining this very well.
I think what you might be trying to ask is, this diagram is illustrating how lookups work for different hypothetical elements. The ones on top are yes instances of a pre-existing street sleeping.
Oh.
And the one on the bottom is an example of how a hash function assignment might be a negative loop. Because you can take all 3 different lookups, check those locations, and you can fit the logical AND of those bits as Boolean, and you say, is it there or not?
So if you will have 3 ones, then it will be kind
It'll
of
be a yes,
somewhat
which might
positive.
be a true positive, or it might be a false
Okay,
positive.
and if there is at least 1 0, then
So it's a true negative.
and you
Yeah.
line each
Yes.
arrow.
Yes,
is
it's a
different,
bitwise AND of the lookup.
but each arrow is
Yes, it's a different hash function.
So if if we had written W, if W was up there and we'd written it to the filter, this would have been, all of the arrows it points to would have been set to 1. So this right here is supposed to represent a read. So we're not actually modifying anything. We're just querying the same bits that would have been written had we inserted W. So anyway, it's I guess a little bit fraught, but I hope that makes sense for the most part. So for this library, I'm using a slight variant of the traditional Bloom filter, and it was a paper was written by Yan Kiao, and she named it Bloom 1, or they named it Bloom 1. And the difference between from the traditional Bloom filter is we first use part of our hash to map to a single machine word. In other words, if you have a 64-bit machine, a machine word is going to be 64 bits. So you map to a single word in your array, and then from there, within that, you use the rest of your hash to come up with, say, 3 bits within that word that you'll set. So the difference is, whereas in the traditional Bloom filter, if you have if you're using 3 bits, those bits could be spread out arbitrarily across your array. Whereas with Bloom 1, you're guaranteed only 1 memory access. So every insert only accesses a single machine word. Did you have a question? Yeah, exactly. Yeah, so you use part of your hash to find your tiny Bloom table and then insert within it. Yeah, and so this works the same, except that it has, in general, like a slightly worse false positive ratio. But all of the, I mean, it's just kind of, it's hard to kind of determine whether that's okay or not, like, unless it's based on your application, but it's pretty like minimal, the difference. So this is better for us, first of all, because we have fewer cache misses. We're only operating on a single cache line. We have fewer like expensive atomic operations, which put even more pressure on your memory subsystem. And so the most important reason why I chose this, though, is because without it, so what it lets us do is when we're concurrently inserting elements, if we only have to go to a single machine word, it lets us determine if the insert was successful or not. In other words, if another thread raced and inserted the same element. So without this, there would be no way of inserting, the word, some word, and then determining that another thread had not already inserted it. Did that make sense how I explained it? Okay, so, and like an example of an application where you might want this property or need this property, say that your users you want users to pick their username for like signing up for your app or something. So you might have your Bloom filter be storing all the usernames that you've seen. And so you can, the user will like query for their username, and you can quickly say, you either like insert it, or you say, oh, it was already inserted. And because you have this property where you don't have these races, what you can do is you can insert it, and then if it was successful, you can like dispatch some really long-running like expensive operation or something, and you don't have to, in that like back-end part of your system, you don't have to worry about you don't have to worry about like 2 users having the same username, doing all that stuff. Yeah. Yeah, thanks. I think I jumped ahead of myself. So what my library does is it makes like a thread-safe version. And so the way that we notice whether we failed or not is by using an atomic operation on that word. So we're able to basically insert and then get back the old, atomically insert and then get back the old value before we inserted. And we can inspect them and see, oh, that old value already seemed to exist there. Or we can see, oh, like one of the bits was missing, so we did successfully insert to them.
I may be pressing in on another tiny detail, but under one model of concurrency, you may have nothing to do with the actual machine. You still shouldn't be a problem. You just overwrite a one.
Yeah.
So it doesn't matter. There can never be interference under my mistaken model of a one. It doesn't matter if it's string. That may not be how the machine works.
Let him describe what he's doing in that. Sure.
Right. Well, if you can imagine, so you have to, in order to do that right that we showed in that that illustration, traditionally you need to read the word, or it with the bits you want to set, and then write it back.
Okay.
So yeah, so there might be a machine that can like, well, it would be atomic, but can like atomically like set bits or something. Atomic set bit, like an operation called that. Yeah. Yes.
But the other thing, which I guess might not have been clear, is that this is like kind of doing another operation that wasn't in the interface, which is basically inserting something additional on being certain that it didn't already exist.
Yeah.
Ah.
Well.
That's something that can fail because that's part of the contract that operation that can fail.
Yeah, although if it's already there, inserting is, idempotent, so it's sort of, yeah, but you're right, yeah. I appreciate the questions too, thanks.
I don't understand movement, so that's something. It seems to me that the original description, collisions of any particular hash, do not do that. That's basically hashes. Here it seems like collisions of any first hash, that you the one that identifies the word.
Mm.
Wait, there's lots of collisions inside of that, because you quickly cannot go out.
Yeah, that's a very good point, and it kind of ties into why I wrote this other hashing library too. Although I hadn't thought about that problem specifically or necessarily. So yeah, good point. All right, so here's the libraries that we use. Basically, there's just these two. There's one called primitive, which sort of just wraps some GHC low-level stuff like mutable byte arrays and some kind of constant machine constants. And then atomic primops implements some of these operations that I've kind of been hinting at, and I'll go through some of the API of atomic primops. But the atomic primops stuff is kind of backed by very, very low-level operations that your hardware supports. Okay, so this is kind of what we use from primitive. So it implements or exports these byte arrays and mutable byte arrays, which are the same, represented the same way, but byte arrays are pure. You can't write to them. So these are just arrays of bytes, which means that they're not. They don't have like garbage collected elements. However, the garbage collector may move the entire array and clean it up afterward. So it supports creating these byte arrays that can be pinned, which means that the garbage collector won't move them. And so you need to use pinned byte arrays when you're doing stuff with the FFI or you're kind of whenever you're going to be passing a pointer around. Oh, okay. Yeah, so cool, okay. Yeah, I actually don't have much experience with like doing foreign function interface stuff, but yeah, so pinned just means it won't move, and then you can set alignment and stuff. You can freeze and thaw between byte arrays and mutable byte arrays, which is just like a no-op. And it's kind of for library authors to use very carefully to be able to use mutability and then present back to the user like a pure array or something that they can't that is not going to be modified behind the scenes. Yeah, so it also implements or exports constants, so you can depend on stuff like the machine word size and alignment and stuff like that. And so this is a bit of the atomic primops library API. These are just a few of the interesting functions it exports. So this first one, cast byte array int, is a compare and swap, which is, there's a lot, like if you read kind of the literature of concurrent algorithms, they use compare and swap a lot, and it's supported across a lot of architectures. And basically the way that operation works is you give it a location in an array, you give it what you expect to be there, and you give it the new value you want to set. And if the value you expect matches, it'll atomically set. Otherwise, it will not, and it will report that back to you in some way. And so you can see if you're using that on an operation that you need to succeed, you will need to use that in a loop and keep retrying until it succeeds. So this fetch add int array and fetch or int array, those I think are only supported on Intel architectures, and they also, I found they perform really well under contention, and they always succeed. And so basically the way that this works is you give it a location in the array. In the case of fetch add int array, you give it the value you want to add, and then it will do that, and it'll return you the value before the addition. It should work on LLVM backend, but I don't think that, I'm not sure what architectures support this actual operation, this underlying promote. Yeah, so I think these will fall back to a compare and swap on when it's not supported. So this fetch add int array corresponds to an Intel instruction, an atomic instruction. So the one that we use is fetch or int array for inserting. And so basically we, to insert in an element atomically, we create a word that has those 3 bits set, and then we say, okay, atomically or this on this part of the array, and then it'll return us back the value before we ORed it, and then we can kind of inspect that and see, like I mentioned, that's how we can see whether it succeeded or whether another element had written previously. Yeah, so just wanted to go through the library a little bit. I'll kind of give an overview of the API, just jump around to different implementation things that are interesting, talk a little bit about testing, talk a little bit about linearizability, which is a kind of a concurrency concept that's really useful to know. And then just talk about something I learned about kind of writing equations, implementing equations in code in this project. It's a very mixed kind of set of stuff. So here's the API. So just to create a new Bloom filter, you pass it a SIP hash key that will be used by our hash function, which is called SIP hash, which I'll talk about later maybe. Insert and lookup, we give it an element that's hashable, which means we can hash it, and it'll return. For lookup, it'll return whether it was in the Bloom filter, and then for insert, it'll also tell you if it was already in the Bloom filter. We also have these union and intersection functions, and they basically write one. So the union function writes kind of all the elements of one Bloom filter into the other, so it's mutable. And likewise, intersection takes the intersection of the 2 Bloom filters, makes the second one the intersection of the 2 Bloom filters. We have a clone function that just copies a Bloom filter, and then we have these serialization functions. So I'll go into what stable hashable is, I think, but basically that class is a class of hashable types for which we can kind kind of version. So basically, stable hashable lets us tell if we're able, if when we deserialize a Bloom filter, if when we try to hash new elements to it, if whether those hashes are actually valid. So it's basically a way of like versioning the hashes that we're using. So this is tricky because I can't see, and I can't see my notes. So, all right. So this is creating a new Bloom filter. So we give it the key, the number of kind of bits within a word, and the size that we want. The size we give it is as a power of 2, which ensures that our actual array that we create is of a power of 2 size, which lets us kind of get to a pointer to the member word we want easily, like by using a bit mask. It basically lets us do like bitwise tricks to kind of find the words that we want in the array. Also, like an aside, you can't, when you're doing, I guess, this kind of stuff and you want it to be fast, you can't really expect GHC to do a lot of the optimizations that you'd expect from a C compiler, just because they're not implemented. So what they call like strength reduction optimizations, like converting a multiply into a shift when possible and stuff. GHC doesn't do a lot of that. Yeah. Right. I should say LLVM will do that kind of stuff. So another thing this function does is it looks to see if 64 hash bits are enough for us to do what we want. And so that depends on how big of an array we created and how many hash bits we asked for. So if 64 bits is enough for us, then we can use a faster 64-bit hash function. Otherwise, we need to use a 128-bit function.
How much memory would a hash for the array that is 64 bits of hash look like?
Like, at what size do we need to use 128 bits, you mean?
Yeah, like, is this going to be like a terabyte or?
No, so it also depends on how many words you want. So like, if you want to have like, so for every bit in your word that you need to set, you need, I guess, 6 bits to point to 1 through 64. 5. Anyways, I don't know. And so if you ask for like 10 bits within a word, you're going to need 50 bits just for all of those. And I know this is kind of hard to, without kind of an illustration of what I mean exactly, but we create a new pin byte array, which, like we talked about, it's not going to be moved by the garbage collector. It's also required for some of the things we want to do, which I'll show later. We also, a little trick we do is we create it big enough to accommodate the metadata that we'll be using for serialization. So when we serialize a Bloom filter, we store like a lot of, all the parameters we need to like reconstruct it. And so by doing this, by just keeping that extra space in the array to begin with, we can create like an unsafe serialize function, which is going to be really useful in certain contexts and doesn't require like another copy of this big array that we created. I think that's about it there. Yeah, so here's our serialization functions. So this unsafe serialize, I'm not sure if that's exported at the moment. I think it is in like a different module than the main one. So it's unsafe in that so we're returning a byte string, and it, you know, you're probably familiar with the byte string library, but it's just a nice interface over you know, strings of bytes. So that unsafe serialize is unsafe because if after we call it, we continue to modify the Bloom filter, we're going to break referential transparency. So the byte string is supposed to be a pure interface. So if we modify it in the background and then you know, we break Haskell or whatever. Yeah, and so this stuff on the bottom, this PS and foreign pointer and stuff, that's all, well, PS that's the byte string constructor. So this is looking at the internals of byte string. It's using we basically, unsafe serialize here is not really doing much of anything. It's basically we're asking for a pointer to the byte array, and then we're like just wrapping all this stuff, and then returning a byte string. So this foreign pointer is like one of several ways of kind of representing a pointer to memory. I guess another little internal thing to point out is that your mutable byte array, so when the runtime will track the mutable byte array itself, that object named mutable byte array, and when it goes out of scope, it can be collected. And so you can't just create a pointer from that and then let the mutable byte array go out of scope. Otherwise, you'll have a pointer to something that might have been garbage collected. So that's why foreign pointer has an address and the array itself, like in it. So this is deserializing, and this is kind of more fraught, I guess, than serializing, because we don't know where our byte string came from. So another thing we don't know is if the offset and length are unset. So basically, like byte string will let you, if you say drop 2 bytes from a byte string, it's not going to actually, you know, make a copy of an array. It's just going to increment that offset integer. So anyway, so here we need to make a copy of the memory in the byte string to a new mutable byte array, which we can use in our Bloom filter. Does anybody have questions about like the internals of byte string or this kind of stuff? I feel like this is kind of not interesting. Yeah.
So how is your clone atomic?
Yeah, so clone is actually not atomic. Well, yeah, no, clone is not. It's not atomic, yeah, but it's safer. So basically, during the clone, elements that are being written to the source Bloom filter may or may not appear in the result. It's not really scary. So I don't know. Maybe I'll go into this when I talk about like, I think it's maybe the next slide. That would be really cool. But when I talk about like linearizability and kind of semantics of concurrent operations. Sorry, this is not it. Yeah, let me get into that more later. Oh, I guess another thing to point out is we need to pass in the key when we deserialize, because I chose not to store the actual key in the serialized array, kind of for security reasons. So if you want to keep your SIP key secret, you don't have to worry about like encrypting that resulting byte string. And that also sets us up to kind of do more efficient memory operations in the future, because we can just rely on that serialized data being, on disk or whatever, being what we're expecting. So we hash the key, and we store the hash of the hash key. so that we can validate when we deserialize. So this is kind of a boring observation, but I found that assertions are really, really helpful, especially when you're dealing with arrays and just like doing math with indexes and all this really kind of fraught stuff. So here's an example, and just using assertions along with your tests. And assertions are also nice because they sort of document invariance in your code and they're runnable. So here's an example of a helper function I have that's it's basically just a right shift, but it checks these various invariants, and that all disappears at compile time. So the compiler will remove all those asserts if you compile with optimizations. Another little trick I do in my libraries now, it's really weird, I guess, but I create this function that's hidden except when we're testing called assertion canary, and this goes somewhere in your library code. And what this basically does is it checks to see if your library was compiled with assertions on. So when you're running your tests, you can test that, okay, yes, the library is going to be checking my assertions. And so I found that tests along with the assertions in your code is it's found a lot of actual real bugs and also helped with development a lot because you catch them much earlier. Okay, so this is an interesting property of Bloom filters generally, is they can do this a lossless union. And what I mean by lossless is that you can take the union of two Bloom filters, and the resulting Bloom filter is going to be exactly the same as if all the elements had been written to that originally. You can also take, and you do that with an OR. So in the same way that you insert a single element, you just kind of OR all of the bits together like a zip. So they also support an intersection in the same way, which is just the AND operation. However, that's lossy, so your false positive ratio will be somewhat worse than if they had originally been written to the original Bloom filter. And this works even for filters that are different sizes. So if you have one filter that's 4 machine words long and one that's 8 words long, to combine them, to union them, all you have to do is kind of fold the bigger one in half on itself, so union it with itself until they're the same size, and then union those. And so what you kind of have to make sure to do there is to make sure that the way that you're taking the hash bits you need to find your word in the filter, make sure that they kind of preserve the lower order bits. So if you hash an element, so this is supposed to be illustrating that. So that row of bits is like a hash of your element you're inserting. And in the red, so the blue bits, those 7 bits there, are for inserting into would be used for a larger Bloom filter. And the red ones would be the only ones that were needed for a smaller one. And so if you can make sure to take take your bits in that way, then you'll be able to hash an element and look it up in the smaller version of the Bloom filter. I don't know if that was very confusing. Probably. Does anyone have questions? I can move on. Yeah.
What's the use of that? Just what would you do?
I don't know. I don't have a good use case. It's kind of interesting. Any property? Oh, yeah, right. Right, you're saying do you have false negatives and false positives now? Right. Yeah.
The other thing is, how does the intersection size quantify the larger one
making oh. I see what you mean, I think it would be much worse. Well, maybe not, I don't know. I think it would be worse, but I don't know. I can't wrap my head around it right now. Maybe so. I'm not sure. So we can maybe check that with I guess one of the library functions I didn't show was a estimation of the false positive rate. I guess I'm going to talk about that if I have time. So we can kind of play with that maybe and see what it looks like. Oh yes. So you have to make sure that they're right. So, and this is something the library does, is it makes sure that all the parameters that the Bloom filter was created, aside from the size, are the same. Right. So, so if you're using two different hash functions in each of the Bloom filters, you'll get kind of a nonsense sort of intersection. The union is kind of makes sense. Actually, you might be able to do something with that. So yeah. Oh, so I think this is where I was going to talk about linearizability. So basically, while we're, and Carter, I was trying to explain this to Carter a little bit. So during a clone or during a union, so when we're unioning Bloom filter A into Bloom filter B, if we're inserting into Bloom filter A at the same time, the elements that are being inserted during that union operation that are overlapping, those elements may or may not appear in the resulting Bloom filter at random. So what that means is that you could, if you had inserted A and then B and then C during that union, you could go over to the Bloom filter after the union and then see A but not B and then C. Sure, non-deterministic. And so one way of formally stating what I just said, and I think it's in the library docs, is you can say that the union is not linearizable with respect to inserts. Is this about? Yeah. Okay. So linearizability, I think, is a really helpful thing to have a little bit of a understanding or intuition about especially when you're trying to design your own concurrent algorithms, which I'd encourage everyone to do. It's not an impossible thing to do at all. So it's a simple way of thinking about the correctness of your concurrent system. And the basic idea of linearizability is that an operation is observed to happen atomically at some point after it's called and before it returns. In other words, while it's running. So at some point during your function call, if you're dealing with functions, the thing happens atomically. So the insert happens atomically, or the pop from a queue or whatever happens atomically. So this is seems really obvious, maybe, but it's actually a really powerful concept. So also when we say observed, so linearizability is about, it deals with APIs. So it's the way that we observe whether a thing has happened is also through the API. So if it's a queue, we observe the ordering of the writes by the pops of the items off of that FIFO queue. So it's a really good way of decoupling implementation of your concurrent data structure or whatever from the semantics of it. And if you're a designer and you're thinking, so does that kind of make sense about what? No.
But don't worry about it. I'm not following.
Ha-
That section is supposed to turn head out.
So what about just the idea that an operation happens atomically, like during the run of like? Well, a transaction is usually is atomic. So yeah, I guess so. I don't think transaction is really the right word though. So.
Could I propose an understanding, and you know if it's correct? I want to define the question, but I just want to try this out. If it's like the database concept. Right? The problem is I've got the 4 threads, and they're all doing operations A through D at once. Linearizability is the threads start. They all try to do their operations at once. Eventually, everyone's done. I look at the final state, and there must be some combination of A happened, then C happened, then D happened, then D happened. There must be some permutation on the operations that happen concurrently that can account for the final state. And if you're not linearizable, that means that no sequencing of operations that are sort of conceptually atomic can explain how you got to the final state. So there's no path of reasoning that can get you there if absent a notion of concurrency.
So another way of using linearizability to reason about an algorithm that you're designing is that just to think that to realize that overlapping operations can happen in any order. Does that make sense? So if you have,
What Gershon said.
yeah.
But if something is non-linearizable system, then the things all come in there, you don't know what's going on. At the end of it, you look at the result. You repeat. Suppose there are only 2 things going on. If the first one happened and the second one happened, you get a certain result. The second, if the reverse happened, you get another. But the thing you get is neither one of those. Then it's called non-linearizable.
Mm-hmm.
But if it's always the case, I'm just in the case of 2 operations. 2 operations. So operation A occurs, then B, you get some result. You get a different result, B happens, and then A. But your system is linearizable. If whenever A and B are coming in, you don't know which is going to go first, but you could imagine it's one or the other. And it's non-linearizable. Look at it, and you look, well, let's see, can I get this via A, then B? No. Well, let me try B, then A. No. No. If there's neither one, then it's called non-linearizable. That's my idea.
And you might have non-linearizability if you write code on x86 and then try and run it on.
Okay. It might have not linearizability if you had code on an x86. Full stop. That's
But ARM is
processor semantics are not linearizable unless you want to memorize that.
Yeah.
Okay. So this is the linearizability you're talking about, right? Or not?
Yeah.
Okay.
Well, so I think there's various ways of using that word, some of which are more confusing to me than others. So like say like linearizability of a system or like proving linearizability of a system, that's kind of more difficult for me to understand. But like talking about understanding how operations relate and whether and basically like if you're using linearizability to understand whether the algorithm you're implementing is correct, it makes you realize that if like say 2 inserts are coming in and they happen to overlap, as a implementer, you're free to actually, you have a lot of freedom there. So you can actually reorder them as they come in. You can see that A came in, you know, if I'm talking, you're inside an algorithm right now. So say you're inside a queue and you see A came in, then B came in, but you haven't returned yet to the caller. You can reorder those if you want. You can even delay arbitrarily. You can like hold open your connection, whatever, for a second and wait for more things to come in and buffer things. And none of those things change the correctness of your algorithm. So instead, when you're kind of implementing concurrent algorithm, it's really easy to think in terms of the actual like atomic operations you're doing on data, when those things can be very different from the kind of so for example, if you're making a queue, you might think of writing to the queue when you're designing your queue. You might think of the queue write as when you put an element onto an array. So maybe your queue is backed by an array, and in your mind you're thinking, okay, like this came in first, I have to put this on the array, and then because it's on the array before this other thing, it's in there. It's in there before this other element, but really that's too low level. So you might be able to put things in different orders in your array, but then your lookup would be able to see a view that represented a correct history of the interleavings of your inserts. So I think I should just move on from this, because math. So this is just a really another like really useful thing that I learned over this project. So this is the formula for the false positive rate of the Bloom filter in this this variant that I'm using, and so it represents the false positive ratio based, given different parameters and given a certain number of elements that are in your have been inserted into your queue. So I didn't understand like the derivation of this. And also, so also to define what false positive ratio means in words, it's the percentage of queries for elements that are not in the Bloom filter, which can be expected to return positives, which are false positives. So anyway, this is not terribly difficult. I actually wasn't familiar with this combination notation, which are the big parentheses, n over x. But it's basically like about how many combinations of things of a different size of a number of a set that you can make. So my goal was to translate this into Haskell so that we can run it, so that we can see, like, users can get an estimate of the false positive ratio. So I don't know right now. Wait, I can probably tell from if we figure it out from the slide. But these are basically like things like, so W is the number of bits. Yeah, W might be word size, or it might be log word size or something, log base 2 word size. N maybe is the number of elements in the filter. Sorry?
Maybe it would be easier to figure it out.
Yeah, it would. Yeah, so remember that and then figure it out like yourself, I guess, from this. So this is the translation directly into Haskell, and it's pretty, like, it's nice. It's pretty readable. If you're familiar with that notation, you'd probably be able to see it's like correct, hopefully. So, like, question time. Can anyone tell me things that are wrong with this? Okay, because I didn't do bang patterns on the. Okay, not having to do with that strictness. No, it's so it's a fair translation from the equation. That's kind of along the. It's not stable. It's very unstable, actually. So. Yeah. So okay. So the minor problem with this is that factorial is, we don't like the complexity of it. Like, this will probably never terminate on a lot of inputs we'd want to give it. The major problem, which is a correctness issue, is that because of all these factorials and these big multiplications, we get arithmetic overflow. So we're using, there's values through the course of the calculation that are greater than we can represent with our types we're using, floats. Huh? Yeah. So Carter had struck on the idea, which is the thing I learned and wanted to tell you about. So did that make sense about the problem with this? Is there just values are going to get too big, or too small maybe also, which is also too big. We call it underflow.
Could I just try to state again, if you look at combination, just for my clarity, the issue is fact and over this other fact should be within a relatively small size, but then the factorials themselves can get enormous, but then the ratio is going to be okay.
Right.
But we have to calculate these huge things just to cancel them back out again, and passing through that will lead to overflow.
Yeah. Yeah. So and I didn't really notice that at first. I was like, oh, like Haskell's so easy to do math in Haskell. But like, so I think I probably tried to run it and it didn't work, and then I had to think about it. So
there must be a Haskell library that does the binomial coefficient.
Actually, some of these combinations are binomial coefficients where Haskell's triangle is actually using the whole row. Probably the fastest way to do this is to actually choose Haskell's triangle coefficient.
There's another thing, just please forgive me. The formula here has an implicit dependency, the dependency. I'm not going to go on that, but it's easy enough to read. Something is happening, and then depending on what happens, something else happens. Okay? So in other words, that's ridiculous to use the word Bayes theorem. It's completely crazy to become a magic slogan. But something happens, and you look at what happens, and then something else happens. Compute the probabilities. That's all.
okay, you should give a talk next. Yeah.
Dependent type or functional group.
No, I mean, so what I'm about to introduce is this, like doing this calculation in log space. And when I kind of made that transformation that I'm about to show, like, I think it doesn't like my water bottle. Sorry, put that over there. It's a little like theremin. I can play you. So anyway, yeah, it'd be great if there was like some library that could automatically, in a type checked way or something, rewrite stuff like this. Cool. Yeah, I don't know about that. So yeah, so this is like a trick I learned to avoid overflow. So I've heard it referred to as doing calculations in log space. And so basically what you start with is this trivial, like, kind of, I guess, definition of log, which is saying that if you take b to the power of log base b of x, that's equivalent to x. And then you use these log properties you learned in high school or whatever to transform your function. So you can see how on the left side you have multiplication, that x times y. If you distribute that log out, it turns into addition. And then similarly, division turns into subtraction. Exponentiation turns into multiplication. So the magnitude of all your operations decreases. And so basically what you do, over here, x represents that Haskell code that I put in. So you say b to the power of log base b of that expression I made. And then you work through these. So if that expression started with a multiplication, you could distribute that log b xy into log base b x plus log base b y.
The library for this, or actually at least two on Hackett.
Yeah?
Yeah.
Cool. Good.
Oh wait, you didn't do that?
Glad I did all that by hand. No.
Then you probably got artisanal code.
Yeah. So does that make sense? Cool. So I think I'll just show. Oh, okay. The other thing I do is.
Whoa!
The other thing I do is we can approximate factorial with this thing called Stirling's approximation, and we try to do that where it doesn't affect the outcome too much. And I don't really know. I don't have much to say about that. It's just something you can read about online.
It was discovered by an early Haskell programmer 300 years ago.
Yeah, no one knows much about him. So yeah, so we take the log of Stirling's approximation because we're distributing the logs all through our thing. So this is like what the transformed version looks like, and you can see we do that log transformation under that summation. That's where we start it. So we're doing the like natural logs. So we do e to the power of log our code, and then we do that log thing over all the like components as much as we could, and then everything got kind of reduced from multiplications into additions, and nothing overflows. So then the code works. How much time do we have, Christian?
Wait a second. I'm not getting one part of this. What's the logarithm of 0?
Good question.
Okay, I just want to...
Um,
No, don't worry. I'm poking.
yeah. So it's funny because when I copied this, there's a to-do, is this right there? And I covered it up so as not to like invite questions like that. So, hey Gershom, how much time do we have? Okay. Cool. Well, like everybody just eat pizza. Someone like do the hook thing when they need me to stop talking. Okay. All right. So yeah. So this is the other library that I've been working on. It's a hashing library to support kind of the requirements that I determined I had from working on that Bloom filter that I've just been talking about. So I'll just go over like the motivation. Go through the library a little bit. This little trick of translating bitwise assignment operators, which is fun. I learned from Oleg. It's like not my own trick. So yeah. So first of all, the main requirement I had, we need to be able to trust that the hashes that we're getting from our library are good, in the sense that we should be able to take any portion of the bits from a hash and kind of know that they're just as like mixy as other portions. And so our question from over here was about like how if your choice of if the hash part of the hash you're using to map to your machine word is not very good, and that could be really bad news because you might, be mapping to a very small domain of your whole array or something. And so, so this has to do with both the hash function you're using and also how you draw bytes from the kind of algebraic data types and just all the data that you're trying to hash and how you combine them. Okay. So Hashable, the library that's like pretty standard, it doesn't do a good job of enforcing this property. It's kind of, it tries to be as fast as possible while not like I think noticeably like breaking hash tables. So it does a lot of things like it'll hash an integer to itself. It kind of mixes hashes in a kind of not good way, I guess, and does various things. So anyway, I don't know how to like statistically analyze this kind of thing, so to experiment. Yeah. Yeah. So there's a couple like avalanche and bit independence. There's a couple ways of naming how mixy a hash is. So anyway, so what I did to kind of determine if, or just kind of experiment with hashable and the mixiness of the hash functions, I did a little visualization. So basically what this does, what I wrote is some code that maps your hash function into like pixels, 64 by 64 pixels, and it's using a space filling curve, so you can hopefully see if there's like, you can kind of maybe see other patterns that way. And it darkens a pixel every time. So 64 by 64 is not enough to like cover the whole domain of your, 64-bit hash. So we darken a pixel every time we map onto it with a hash value. So this is basically what right here showing, visualizing the hashes of that tuple, a 3 tuple of bytes, a word 8s, which has 16 million possibilities. Hopefully that's the correct number. And so we can see this looks pretty random. So also red means like clipping, so it meant like we got to like, as black as we could go or something. And so this looks like white noise. It's good. This is my library. It looks good. So so this is I'm really cherry picking like a bad example that I found. So this is what hashable looks like when it.
Are you saying it's the identity function on int?
Sorry?
It's the identity function on int, isn't it?
Yeah, for ints, that's what it does. So this is kind of showing how the ways that it's combining product types is not very good. So you can see how there's a lot of clipping here, and there's a lot of white space where no hash values were written to. Well, so no, but yeah. So I'm kind of working on this hashabler, making it faster and maybe work better, and maybe eventually it can be become a replacement. So so like I said, this has to do with kind of the way that, possibly with the way that the actual hash function that hashable is using. But mostly this has to do with kind of the way that it's producing bytes from algebraic data types, which is something I'm concerned with. So, I should also note that like if you give hashable, like words or like text or like probably any like realistic example, it doesn't look like this. So this is pretty, somewhat artificial. But it's still a bit scary if you're relying on kind of your hash for the kind of properties, complexity properties of your algorithm. So, so the second thing because Bloom filters are so easy to serialize and such a kind of useful thing to be able to serialize, and like we can combine them and like you can use them in a distributed setting. We want them to be able to be consistent across architectures. We want to be able to store them, maybe read them back later with a maybe slightly different version of our library. And so so hashable doesn't make any promises about that, and the hash functions that it uses internally have changed, depending on what has been faster. So that was just kind of not going to work for us. So we also wanted to, in addition to kind of just trying to be stable, we try to make a version guarantee, in our package, hashabler package. Like we try to actually say like, okay, if we change, how this certain instance will like bump the major version or something like that. Like an int, yeah. So that's one of the kind of exceptions or kind of sticky points. So what we actually do is I think this is right. So in my library, I think if an int can fit within 32 bits, it will hash the same on 64 and 32-bit architectures. If it's bigger, it won't. So, but if it's bigger and you're using it on a 32-bit platform, you already like have correctness issues, like with your code, I guess. So anyway, that's just some, there are some like points where we can't make that guarantee, and we try to note that in the instances. Yeah, so the other really nice thing we want is we want extensibility. So we want hash function authors to not have to think about like how to serialize algebraic data types, and we don't want them to have to think about endianness or all these kind of architectural challenges. So if you're writing a hash function, we'd love to just be able to give you you know, a stream of bytes that you can fold over to do your hash. And similarly, if you are not a hash function writer and you're just like you have your own like algebraic data type that you want to hash, you want to be able to define, to make it hashable in for any number of hashes that you might want to use later, and so on. So I can kind of show you the actual code, and it'll make more sense what I mean, hopefully. So this is the hashable class, and it's what users use to define hashable instances for their data types. So these are not hash function authors. And it basically defines how to deliver bytes to a hash function. So the operations we can use inside of one of these instances is hash itself, and these set of mix operations, which I'll show you, which belong to the hash state class. So those are the two things we can do inside there. And it's the responsibility of hashable instance. Yes, sorry, yes, same name. This is my own class in the hashabler library. So, I'm sorry? No, and also like future work is to derive. Oh, you can.
Let's try to get this part of the talk.
Sure. I can. Okay. Sorry, I'll try to like speed this up. So it's also hashable instance authors have to be concerned with delivering these bytes in a way that's cross-architecture compatible. So that can be challenging depending on what you're doing. So here's the, these are like trivial instances for words of 16 bits and 32 bits, where we're just calling mix 16 and mix 32, which I'll show you is part of the hash state class. So this is what hash function authors deal with. So they basically, when you define a new instance and when you're writing a hash function, you create a function that's passed in a fold over bytes that are delivered by your hashable instance. And so we have these defaults here, which let you, so the minimum implementation is just mix 8, so you have to basically tell it how to hash in a byte. So that's what mix 8 says. It's how do I hash in a byte? And we offer these other sizes because it can be more efficient to, you know, you might have a hashable instance that can deliver chunks of 64 bits, and your hash function might operate really efficiently on 64 bits. And so if those are available, you can create your own implementation for mixing 64 bits into your hash function. So this is a whole implementation of a hash function. So this is the FNV1A algorithm, which is a very simple hash function that works okay. So you can see in hash state, so our state is very simple. It's just a 32-bit word. Our mix 8 implementation just does this, you know, this XOR multiplies by a magic number. And then this function on the very bottom, this is what we actually export to users. So we can see we call our implementation of hash within it. We basically just have to call it with this initial magic number and then unpack it. And then, so that's our whole hash function. And so we're not concerned at all with like, endianness or how to map over a byte array or a, tuple of whatever. So we also, so we implement that in hashabler. We also implement siphash, which is a, it's not a cryptographic hash function, but it provides protection against hash, as they call hash flooding attacks. So it's basically a hash that you can't predict, which, so there's a lot of reasons why if you're exposing like a hash table to untrusted input, there's kind of nefarious inputs that that an attacker can use to like kind of, do a denial of service attack or something like this. So this is considered like a secure hash function. So the state here, so this is the state of the hash state, and it's quite a bit more complicated. So we even, siphash has to actually, part of the algorithm takes into account the length of the element that you're hashing, and it has these 4 different words that it twiddles and stuff, and we have these other things that are sort of like bookkeeping for the way that we use siphash. And the implementation of siphash is quite a bit more complicated. We have a whole setup kind of procedure, and then this hash state instance is used to actually map over the bytes, and then we have a whole like mixing at the end. But the nice thing is this like hash state, this class that we implement is flexible enough to do both of those. Okay, so this is the little trick I mentioned. So about like translating this kind of code into Haskell. So you can see we have all these bitwise like assignment operators, and this I think this is kind of explicit. So it's actually nice that it's written this way, because if you're the designer of this code, this algorithm, you would see like where exactly you're destroying information and how you're mixing it at each step. But it's like inherently like mutable, so it's sort of weird to translate. So here's like a naive translation of part of that C code. Can anyone, another puzzle, can anyone figure out what's wrong with this? Yeah, recursive lining. So, huh? Yeah, so, so basically, so the problem here is that in that first line, let v0 equals v0 plus v1, that v0 in the right-hand side actually refers to the v0 just to the left. So it's an infinite loop. It's just like a bottom. Yeah, so so what you can do is do this. So you're using the identity monad, which is just like a trivial monad, and you're making use of the kind of scope of bind and do notation. And so this looks really nice, and it was really easy to translate that code, and I didn't have to like do like a bunch of backticks and like count them and like make sure I was matching them. So you just turn off warnings for overlapping for this, or name shadowing for this file, and it worked really well. And you can even like, if you want to do 2 SIP rounds in a row and inline them, you can just copy and paste, and it all just works. It was great. I'm almost done. Oh yeah, so it doesn't, writes don't scale very well, or at all actually. So it's somewhat, and this is all stuff I kind of played with last night. So, every write, entails, probable like cache miss, especially if your array is really big. And so there's a lot of like cache coherence traffic. And so it turns out that if you try to distribute your writes over two threads, it doesn't, at the moment, it doesn't really help you anything. And I think that's because of memory traffic, but it's like future work to kind of look into that and think about how you would build a high performance server backed by a Bloom filter. Like maybe you'd kind of shard or try to like, you know, make sure like one thread is only responsible for like a portion of your Bloom filter. Yeah. Mm-hmm. And also just how atomic writes kind of change the cache behavior would be an interesting thing to know. Future stuff I want to do for the Bloom filter, it would be really nice. I've tried to kind of think about how to add more type safety to the interface because there's a lot of like parameters that have to match up. And so maybe we could use like you know, type level naturals, and there's kind of a lot of kind of trade-offs there. I'd like to play with using mmap for kind of having persistent Bloom filters and sort of lazy loading them. With hashabler, we'd like to make zip hash faster. We can't automatically derive hashable instances yet either. Hey, yeah, thank you, Gershom, for having me. It's a great opportunity for me to try to do a talk and be here to meet people. So also in my company I work for, Signalvine, are hiring Haskell developers. I'd love to talk to anybody if you're, want to talk about the company at all. It's a really great place to work and a cool thing we're doing. So anyway, thank you.